All right, hello everyone. Welcome to App Engine Nitty Gritty. We put up one of those Google moderator things, so if you want to jump over there, tinyurl.com, App Engine Nitty Gritty. Welcome to submit questions, and we'll take them from the mics as well. As people are trickling in here, probably people are grabbing food. Just going to tell you a little bit about what we're covering today. One is that for folks who went to Brett's session yesterday afternoon, he had a session on scaling apps on App Engine. There's going to be no overlap at all with that one. We'll be covering, also things about scalability, but none of the same things. Would definitely recommend his talk, though, if you didn't catch it. So we're going to talk about some things that are unique about building on App Engine, how you can, when you're on a system where you expect to have some errors, how you can build something that's stable and reliable on top of that, knowing that, some of those parts can and will at times fail. We'll also talk about some of the lessons we learned and recommendations about how to make your app scale well. And we'll also talk about integrating external services. In our case, that was Amazon EC2. We'll talk about why we did that, why you might want to do that. It could be a different service, but just looking at how you might have things that don't fit onto App Engine that are important to your app. We are from frontseat.org, which is a civic software company up in Seattle. And we were founded around the idea that software is getting cheaper and cheaper to build, and because of that, we can start applying software to civic issues, things where in the past it might have been prohibitively expensive, but with the falling costs, there really are some new opportunities out there. I'm Jesse. This is Dave and Josh, and I'm the lead developer at FrontSeat. These guys each run their own consulting companies and have been working with us for a long time, and they've been very involved in all of our work with App Engine. I'm going to give you a couple examples of the kinds of things I'm talking about with Civic Software before we dive in. This is a site we did just after the election last fall where Obama had said, I want to appoint a chief technical officer for the country, but nobody had defined what that role was, and so we put up a site really quickly. Took us about a day to launch this and let people submit, discuss, and vote on ideas for what that position should be about, what the priorities for that position should be. So you can see the top result here was about a combination of net neutrality and accessibility. Earlier last summer, we did a site where students who went to school in a state other than their home state could go and say, I'm from this state, I'm at school in this other state, and the website would tell them where your presidential vote will count more. And then it would help them register to vote and get an absentee ballot. So we have a whole bunch of projects. I'm going to skip over these other ones. If you want to know more about the kind of stuff we're doing, you can check out frontseat.org. It links to all these things. Everything from utility bill designs that promote conservation to satire about the payday loan industry. The project we're going to talk about today is called WalkScore. And before we dive into that, the context of all this is that we're a very small team. We have a lot of projects, and we need to minimize our overhead and our maintenance, and that's the context for our use of App Engine. So we wanted to bring a civic software service to scale on a budget with a very small staff, no sysadmin staff to sit around and monitor it all the time. So on to WalkScore. WalkScore is a website that lets you measure the walkability of any neighborhood in terms of access to amenities. So it's how much can you do without getting in a car? And I'm going to give you a demo really quickly of the original WalkScore website. It started out with a Google Maps mashup. So I'm going to search here. You can search for any address. I'm going to search for the Moscone Center address so you can see if our network cooperates. My monitor also seems to be a little bit confused about what size it is, so sorry that it's off-center here. So as these searches complete, it pulls up a bunch of amenities in the neighborhood, and it calculates this score up here at the top from 0 to 100 of how walkable that neighborhood is. So there's a ton of stuff around here. You can do a lot of things without getting in a car, so you get a very high score, 98 out of 100. And then on the side here, you can see things like the restaurants, the coffee shops, got parks, schools, all these different amenities. And we've got integration with Yelp. So if you look at the Yerba Buena, it'll search for reviews and pops up a little picture there. You can click through to the reviews. And we also have Street View. So maybe we wanted to go coffee and see what's the closest thing that's not Starbucks. Jump over here. And I think that's it. Yeah. There's that coffee shop. So this walk score indicates, how much can you do without getting in a car, and it's also an indicator of the vibrancy of a neighborhood. And this part that I just showed you, this is great for checking out a specific address, but what if you want to get to know a city at a larger scale? Well, we did some work where we generated these heat maps that can show you in green the most walkable areas and fading out to red the least walkable. So this is the map for Seattle. You can see, those who know the city a little bit, downtown, Capitol Hill, University District. And then you have these little pockets, these little neighborhoods that are down in Columbia City and West Seattle, where you have some kind of little neighborhood. And this is a great way to get a quick insight into the shape of a city in terms of where people actually hang out on the streets and where the street life is. So why are we doing all this work about walkability? Well, it turns out that walkability encapsulates a whole bunch of great things into one concept that's very easy for people to understand. So a few of those benefits very quickly. Climate, if people walk more, they drive less, they emit less greenhouse gases. Health, people weigh about 7 pounds on average, 7 pounds less on average in walkable neighborhoods. These neighborhoods tend to have strong social capital, good transit options, very few auto-related deaths. Also a lot of economic benefits. Home values tend to be higher or appreciate faster, or in this climate, fall more slowly. And transportation costs are a big part. They're about 18% of household income, much less in walkable neighborhoods. And they tend to have very strong local economies where local businesses can thrive. It's also something that people rank very highly in terms of choosing where to live. They say walkability or access to amenities is one of the top 2 things, higher than property taxes or schools. So what we try to do is create demand for walkable neighborhoods by educating people about the benefits, and then fill that demand by providing transparency about the walkability of every property. And we want to help people find these places and also create more of them. So walkability matters most, and this kind of transparency matters most when people are choosing a place to live. And that means we need to be on real estate sites. So the first thing we did for that is built this widget that is very easy for people to embed. And this is basically a miniature version of what I showed you before. It's just that rectangle part is what can be embedded into a real estate site. And we've seen a lot of adoption of that. We've got about twice as much traffic to that tile as we do to our website. So it's been very successful. But they often put us down in the kind of about the neighborhood section. And it's not really the ideal placement. So what we really want is this. We want to be right in the primary information about a property, 3 bedrooms, 2 bathrooms, walk score 86, and we want search by walk score. And so to do those things, we need to build an API that gives scores back to a real estate site very quickly, so they can just pass us latitude, longitude, and we give them a score. They don't want to wait for all those local searches to happen and all the restaurants to load and all that. So we're going to jump into the tech stuff now, and we'll talk a little bit about why we brought EC2 into the picture, why we didn't just do everything that we built for the API on App Engine. And we'll talk a little bit about some guidance on making apps scale, and some issues that we ran into and thoughts about working within the App Engine environment. I'm going to hand it over to Josh to take us in.
Thanks, Jesse. All right, so when we first were talking about the API, this is pretty much our ideal workflow for the entire API. All we really want to do is have a request come in, latitude, longitude, location, goes through this magic box, spits out a score response. So that's pretty much it. And of course, things get a little bit more complicated than that, but before we get to the complications, we have to figure out where we're going to host this. It's pretty straightforward. We could have run our own servers. And so when we were considering where to put it, these were some of the, these are unfortunately just the negative considerations at first glance of App Engine, but some of the things we thought about were vendor lock-in. If we write code for App Engine, are we going to be able to, is it portable a little bit because it's similar to Django, but we're going to have to rewrite some things in case we had to move. The cost, when we started this and launched it, there was no pricing announced, so we didn't know what we were in for. We assumed here it would be a competitive cost to host on App Engine. And it's a beta product, so we didn't know, is it going to potentially go down for 6-8 hours, make us look bad, are we going to have various other problems? And we decided after all of this that Google engineers probably are going to keep things up better than we would with a series of EC2 or other virtual machines. Cost would be good, and we weren't super worried about the portability of the code. So we went with App Engine. And the next step then is to figure out what I considered kind of that core functionality, and the core functionality is just this. This is really what we need, ability to return responses really fast. So the criteria for us is always, let's go ahead and separate out this core functionality from these other pieces, and I'm going to show you some of these other pieces that we considered secondary functionality. Do we put the secondary functionality on App Engine where it might conflict potentially or cause a problem, so our core functionality of returning responses would fail? Should we put it somewhere else? How do we integrate these other pieces? So I'm going to spend a little time just talking about some of these secondary pieces that we decided not to put on App Engine and some that we did. So App Engine, of course, really, really good for simple operations. Request comes in, does something basic, such as look up a score, return it. Not so good for certain other things that it's just maybe not designed for. Some of these things Jesse mentioned, such as the rankings. We have a fairly complex procedure to figure out the rankings. It's not just counting up points in a polygon for the different neighborhoods and cities. We bring in all kinds of demographic data and weight by population for each walk score. And App Engine's not really set up for that kind of geo capabilities. Some folks I know have done some back-end work with this, but we do all of this offloaded on a PostGIS database. And so that's offline. The other is, what if we just want to look at the API usage? Who's using stuff in a day or a week or a month, and where are the queries coming in? So this is Seattle API usage over a given time. And we want to know a little bit, are people coming in and maybe doing a kind of a survey or an academic study where they're going to request a couple 100,000 points in a specific area? Is it people just looking at houses all over the place, and when? And this helps us decide where to pre-calculate points. We want to make sure we can respond really fast to places, so we seed the API with some obvious things, such as all of the sort of current places or cities. Maybe the top 1,000 cities will score all of the possible walk scores there. But where else do we go next? By looking at the usage, we could see things like, oh, people query for houses mostly within 2 miles of a city center. And also when we're doing the rankings, are we going to rank over urban areas? Are we going to rank over the statistical metropolitan stuff from the census? So we do this offline and then precede the cache offline with places of interest. And all of this pre-calculation stuff brings in a complication to that really, really simple workflow, which is we have to actually calculate the score to give it out. And so the API gets a little bit more complicated. If we don't have a score, we return saying don't have a score, then we have to go do something about that. And to just explain a little bit why we decided to offload the scoring portion outside of App Engine, I'll hand over to Dave.
Okay, so Josh showed us a number of the reasons that we couldn't strictly build the WalkScore API on top of App Engine. And I'm going to talk through sort of the central reason that we had to make use of Amazon EC2 too. And that's that, as Josh hinted at, that WalkScore calculation takes time. Now, calculating the walk score is not CPU intensive, but it is rather I/O intensive. At a minimum, a walk score requires us to make 17 URL fetches to Google Local Search and potentially talk to other services, census services, geocoding, et cetera. Now, if you're an individual user and you go to our website and type in an address, your browser and our JavaScript will do most of the work for you. But if you're a real estate company, what you really want is programmatic access, and you want us to do the work of calculating the walk score on your behalf. And so that's why we built this API. So from a customer's perspective, the request-response cycle, as Josh mentioned, is give us the latitude and longitude, get back a score if we've already calculated it. Otherwise, queue it up. And we've actually built a reliable message queue abstraction on top of the App Engine data store to hold on to the latitudes and longitudes that we haven't yet calculated. Of course, at some point, we have to turn around and actually service that queue. And so we looked at a few options when we were building our API. The first option we looked at was App Engine cron jobs. And as you know, App Engine cron jobs allow you to regularly ping an App Engine URL handler. That URL handler is subject to many of the same restrictions that standard URL handlers are subject to on App Engine. So in our case, making 17 URL fetches is probably not going to happen in the time frame that App Engine request response are allowed. So unfortunately, cron jobs didn't look like a particularly good answer. And of course, the second thing we looked at is whether App Engine supported background tasks. And obviously, if you were at Brett's talk earlier, you'll know that the new task queue API is going online in a few weeks. And we're very excited about that. We believe that we can move a lot of our functionality of our walk score calculation onto App Engine. But 6 months ago, when we started building this API, background tasks weren't available in App Engine, so it wasn't really an option for us. So where do we turn to? Well, we turn to Amazon EC2. For those who don't know, EC2 is Amazon's API to spin up virtual servers. You have full control of the machine. You can choose whatever operating system image you want. And for us, the things that it gave us was a place to do background processing, the ability to do an arbitrary number of URL fetches, of course, just arbitrary I/O since you own the machine. And the design of our calculator is very parallel. We have lots of processes running, working on different latitudes and longitudes, making different network requests. We needed a place to run lots of processes in parallel. So in other words, the walk score API is built with both App Engine and EC2. And when you start to build a service with multiple cloud computing environments, there are a few important considerations to keep in mind. So I just want to show this perspective. Here we've got the customer's code on the left, our App Engine code in the middle, and our Amazon EC2 code on the right. And here's a customer request where we've already calculated the score. They give us a latitude and longitude. We check to see that it's already calculated. We package up a response and send it back to them. And here's the other type of customer request. We haven't actually seen it. The details of what we do on the App Engine side aren't really important, and as Josh mentioned, it's not very complex. But the important thing to see here is that during a customer request response cycle, Amazon EC2 has never been touched. So Amazon EC2 is simply our queue servicing code, and customer requests never get to Amazon. And that's a really important design point that I'd urge you to think about if you're architecting a API for multiple cloud services. For us, what it means is that our uptime and our scalability is not a function of both App Engine and EC2's uptime, or rather our downtime is not a function of both of them. It's only strictly tied to App Engine for us. If Amazon EC2 goes offline, what that means is that it'll take a little longer for us to process requests in our queue. So we've architected this API, and it's been running for the last 6 months. And I want to talk a little bit about the behavior that we've seen during the last 6 months. So this is sort of the bottom line thing that I'd like to stress. And of course, App Engine is a beta service, so some amount of unpredictable performance is predictable. But we saw a number of concerning things along the way, which have really smoothed out over this beta period. So the number one thing that we struggled with while running our API in production is high data store contention. And by contention, what I mean is when we make a fetch or a put to the data store, we see a timeout. So contention was the percentage of timeouts we saw in a given set of requests. And in particular for us, where we saw contention was accessing our queue data structure. So obviously, customer requests are coming in at a rather rapid rate. They're adding new latitudes and longitudes that we haven't calculated yet to the queue. At the same time, our calculator is trying to pull them off, computing them, and then pushing them back to App Engine and removing those entries from the queue once they're calculated. So a typical day for us today is about a 0.5% failure on reading from the queue. Just 2 days ago, at around 1 a.m., I think, we saw App Engine contention rise up to about 50 or 60% for about 6 hours. So a really big surprise. Something that we had to architect for on the Amazon EC2 side where we're servicing our queue. Obviously, we buffer up a lot of latitudes and longitudes there so that if we do, or if we're unable to get data from App Engine for a while, we can still continue to calculate walk scores. So another thing that could happen during this, especially during the beta period, is that the data store goes offline or simply goes into read-only mode. For those of you who have running applications, over the last 6 months, you'll know that this has happened from time to time. What you see normally in these cases when you make a data store request, you see a capability disabled exception. Another thing that we've seen a lot is that the App Engine response time increases. And we measured this on the EC2 side. So as our calculator pulls new points from our App Engine queue, normally those requests take about half a second to a second. Every once in a while, the response time goes up to several seconds. So in other words, latency increases. App Engine's a bit of a black box, so it's hard to always understand why this is happening. With no changes to your code and with no changes to your underlying data models, you might see this. And this is a very rare occurrence, but has happened once or twice in the last half a year. So with those performance issues in mind, what can you do to make sure that your application scales as far as you need it to? And so what I'm going to talk about here are sort of the steps that you can follow to make your application scale as far as you'd like. These steps are distilled from our experience building the WalkSquare API, but also building other APIs on top of App Engine that we're working on. So they may not apply in your condition. They're just good rules of thumb to keep in mind as you're building your application. So scalability on any system is really about stair steps. You do a certain amount of work, you get to the next step. To get to the step higher might require substantially more work on your part. And so at the bottom rung for App Engine, when you're just getting your feet wet, here are some of the things that your code might have. So first of all, inconsistent model design. Either your models are very large and you only access one or two properties in them at a time, or your models are very small and distributed, and you end up accessing a cluster of different models in a single request. In that case, you probably want to rethink the design of your models, shape them a little bit differently. So this is a characteristic that I've seen in just starting out App Engine applications, especially for people who've worked in the SQL world before and are just sort of starting to move over. Uneven or no memcache use. It's a lot of fun, and it's a lot easier to write your application without thinking about memcache at first. Unfortunately, pretty much all good App Engine applications are going to make some or very heavy use of memcache early on in their life cycle. And the final thing is, for those who don't know, every time you make a data store request, a fetch or a put, you're effectively making an RPC request somewhere in Google's data center. So you're able to batch these requests, but it can be difficult to design your code that way. So a lot of early stage code that I've seen doesn't do that. So with this sort of naive style of coding with App Engine, we've been able to see something like 5 queries a second handled, which is actually really rather amazing. I should point out that this number is in our experience. Depending on the type of application that you're building, you may see something different. But this is approximately what we saw when we were starting out with the WalkSquare API. 5 queries a second is over 10 million requests a month. It's already really rather large application. And it speaks to the power of App Engine as a platform to get you scaling very fast right out the door. So where do you go from there once you want to go past that 5 or so queries a second? Well, the very first thing I'd urge you to think about is starting to use memcache. And the easiest way to use memcache is just slather it on everywhere you read data from your data store. So the basic behavior, of course, is if you're going to read an entity from the data store, check to see if you've cached it first. If you have, great, you're done. If you haven't, read it, add it to the cache. Oh, and be sure when you're writing back or updating that entity in the data store to either clear your memcache or update it. And if you actually go and look at the Google App Engine cookbook, somebody uploaded, I think about a month or two ago, a really great shim for the App Engine data store that just causes memcache on read to happen everywhere. So as a first step, that might be something to look into. Another thing to think about is to batch your data store requests where easy. Where easy for us was anywhere we had non-nested loops. So anywhere we had a loop that we were putting single entities, we inverted that. Now we call one put with lots of entities. And I should mention that batching is a little bit tricky because you can only fetch up to 1,000 entities at a time from the data store. And puts are limited based on the size of the entities you're putting in the data store. A good rule of thumb is 50 at a time. So you may need to have multiple batches depending on the size of the operations you're performing. So with that work, we saw pretty much a doubling of our ability to handle load, which is actually, again, really rather impressive. And that's not so much engineering work on our part. But we wanted to go a lot further. And of course, the running WalkSquare API sees substantially more than 10 queries a second on any given day. So what do we have to do next? And the next set of tips are really a grab bag of things that you might want to think about as you really scale out your application. The first is that I'd urge you to think long and hard about how your data store is accessed and what type of usage patterns you see. So Memcache is really great in particular for two types of usage pattern. One is repeated requests to the same data, and the other is predictable sequential access to data. So for repeated requests to the same data, if you know your customers are going to hit that same entity again and again, cache on read, like we discussed in the previous step, is actually really a great strategy. But if you have predictable sequential access, for example, in the case of the walk score queue, we know that we're going to pull out those queue items in order. Our calculator code is going to request them in a certain order. So our calculator talks to App Engine, and it requests 50 items at a time from the queue. But on the App Engine side, what we do is we actually pull out a full 1,000 items from our queue, put that entire list in the Memcache, and that obviously cuts down substantially on the number of data store accesses we need to make. So think about Memcache usage patterns. Batch all of your data store calls. This went a long way for us to scaling outward. And for us, what that meant is unraveling nested loops. Sometimes they were loops that were basically across method boundaries, so we had to flatten a lot of our code at. But it really helped us a lot. As important as using Memcache carefully is, sometimes it's just not the right thing to do to use Memcache. Depending on your access pattern, Memcache may not provide a very meaningful barrier between your users and the data store. And Memcache is a limited resource. You obviously don't want to populate Memcache with entities that aren't useful to you and lose the entities that are. And of course, Memcache, when you add items to Memcache, you can, of course, think about how long they stay there. Sometimes that's a very great way to keep Memcache pressure low. And then I would urge you to load test your application. We actually built a load testing harness on Amazon EC2. We're able to hit our running walk square instances with over 100 queries a second. And that's real load, talking to real URL handlers that actually do real work with the data store. So load testing. There are third-party products to help you with that, too. App Engine load tends to be surprising once you get pretty high, past 10 queries a second. And the last thing is, of course, monitor your performance. Now, the front line of defense for monitoring performance is the App Engine dashboard, which is a great place to go, and, of course, your logs to look at individual requests that, for example, gave you a data store timeout. Also, the system status, if you're seeing a lot of latency, is a good place to go. Just look at the overall behavior of App Engine. We actually built our own performance dashboard for the walk score API, which we're happy to show you if you'd like after this talk. And it monitors specific things about the behavior of our EC2 calculator code communication with App Engine. And just sort of one last technique if you're getting started with App Engine coding that I think everybody should know, which is if at first you don't succeed, try again. What we have here is basically an attempt to write to the data store that if it times out, we're going to turn around right away and write again. Just a few milliseconds later, you may not get a timeout exception. And this is something we do everywhere in our code base now, both on the read and write side, and it's actually extremely helpful. So I've talked a little bit about general principles for scaling out App Engine applications. And what I want to do now is turn it back over to Josh, who's going to talk about one specific instance where we had some difficult scalability issues that we needed to tackle and the sort of unorthodox technique we used to solve them. So thanks.
Thanks, Dave. So yeah, I started out talking about kind of the core functionality and secondary functionality. Obviously, your guys' applications are going to have different pieces of secondary functionality that may or may not fit different places. A really common use case on App Engine is counting stuff. I'm going to talk about a specific issue we have counting our users' requests. We have a basic quota system. We have an API key. We want to know who's basically doing what. So certain folks might get a couple 100,000 requests a day. Others might get maybe a couple million a day. But we want to make sure that people can't just run away and abuse the system. And again, we understand who's doing what where. So counting every request that comes in, matching it to a user, should be pretty straightforward. And the answer that's usually given for this is, oh, just use sharded counters. Every time a request comes in, write it to one of these shards. You're good to go. But every time a request comes in, if that request is 100 requests a second, that's a lot of shards, and you're going to really hit a lot of data store contention. So we found that these sharded counters didn't scale as well as we had hoped. And what happened in our case, this was from about 6 months ago, and things are a little bit different now. Around 30, 40 queries a second, our response time started creeping up, 2, 4, 6 plus seconds, and then along with the error rates, and then all of a sudden, everything was 503s. And this is a really big problem because, again, core functionality should not be hurt by this sort of icing on the cake of counting who's doing what. So we were finding that just because we wanted to have a quota system, now nobody can even get a score because all the requests are just bombing out entirely. So the solution that we came up with, how many of you guys were in the talk just before this, Brett's talk next door? So a few guys. So one of the things I thought really interesting example of the new task queue was the back-end sort of writing to a cache. We implemented a similar concept. Dave talked a little bit about using memcache cleverly on read, and this is using memcache on write, which in the Google group discussions and other places, people generally say, oh, don't do that, memcache unreliable, things might go away. But in my opinion, there are certain cases, and this is one of them for us, where you don't absolutely need to have exact accuracy. If you're writing a banking application and counting people's pennies, don't do this. But for a lot of cases, if you're just getting a general idea of a quota, how many things are generally around at a given time, and again, knowing things might fail, you have other processes to come in place and check things happened accurately, do things twice, and so forth. Using memcache on write can be a really interesting idea. So this diagram basically shows that request comes in, we hit the API. Rather than writing to a sharded counter, a data store counter, we write to these sharded memcache counters. When the memcache counters fill up to 100, 200, whatever, only then do we write that bit of information to the data store. And then the task queue is a little bit nicer than this. In the talk just before this, you noticed between the memcache and the data store, there's this task queue. And it's a lot faster to write to the upcoming task queue that we certainly weren't expecting when we started writing this. But you still have the same issue writing to a task queue or writing to the data store, which is there's a small time period where requests can come in, hit your memcache shard, increment the count before you've written and then cleared the memcache shard. So you just have to sort of keep track of the delta of what you were writing to the data store and then the amount of things that came in before you got confirmation. Same with task queue. So as I mentioned, the solution's really nice. The advantage is really nice. You get, instead of 100 data store hits a second, you get a couple orders of magnitude less, and that just scales up really, really, really nicely. But the disadvantage is there is I don't know where my disadvantage went, but there's the possibility you could lose a little bit. And so for our use case, we were okay if it was off a little bit as long as we didn't overcount. We didn't want to accidentally set someone over a quota that they didn't use. And so we're just really, really careful that in case of a loss of data, it's always a subtle undercount. And again, memcache has proven really, really reliable. There's a couple of 2 or 3 hour knockouts that we had that we just lost counters for. But aside from that, as a general rule, you can pretty much rely on it. So after we implemented the memcache, things went like this. And again, this graph's from a while ago. These days, it's smoother, and things stay well under a second for the response time. But it's really a huge difference. What it means is we can actually count stuff now at a very, very high rate per second and not have to worry about hitting these issues where our core functionality is compromised. So the summary here is it's not necessarily a bad idea to think about using memcache on write. Again, possibility of lossiness is always there, but in many cases that you might come across, it can really save not only the possibility of this data store contention, but also some money, because you're charged for the CPU time on the data store, and if you're not hitting the data store, that can add up a few bucks a day over time. And then the other piece is early on, decide, is this functionality a good fit for App Engine? Certain things, for example, we could have offloaded the quota, parsed logs every couple hours offline, come back on, and we decided, oh, this is a good piece to fit on App Engine. We ought to be able to count stuff. Other things we decided, no, this piece, although integrated with App Engine and the API, maybe we'll move off. So just deciding which pieces fit in App Engine is important. And then the final one is, of course, when you're putting those pieces into App Engine, make sure that you write them in such a way that should strange and weird things happen, like all of a sudden you get popular 80 queries a second, data store contention hits. Those features that you wanted to have in App Engine don't compromise the really core functionality that your application may have. And so with that, I'll turn it back to Jesse and talk about some of the overall results.
So you've seen some of the stair steps to scalability hotness that Dave went through. Where has all that gotten us? Well, the three of us, very small team, have built an App Engine API that handles over 1.5 million requests a day and peak rates up to about 80 requests per second, so quite a bit higher than where we started. And we've come to think of App Engine as really being a black box. It's a place where things may shift in unexpected ways internally, and you may not always know what's going on in there. But it's also very well documented, and not just the main documentation online, but also this dynamic support with the IRC channel, the Google groups, the issue tracker, and the App Engine team is really they frequent all of these places. So the degree of communication is pretty amazing, and it makes working inside of a black box considerably less daunting. So our amended statement would be, it's a very good black box. I think looking back, we would make the same choice that we made, not knowing a lot of the things that we've learned along the way. And I can say that having watched App Engine progress over these last few months, the work that we've done would be considerably easier starting now than it was starting back then. So we hope that this talk has helped you understand some of the risks and rewards of using App Engine and some things about how to get your app to scale well. I'm going to put up our contact info for a second here, so if you want to get in touch with us, you can jot that down. We will also, got some time for questions here, and we also will be out at the demo spot for most of the rest of the afternoon until about 4 o'clock. So if you want to catch us there, please do. And we'll move into Q&A now. So we're happy to take questions on anything. We'll take them at the mic, and also I'll flip over to the moderator site in a few minutes. But before I do that, I want to put up, these are a few things that we didn't put into our talk, but we definitely have more to say about. So if any of those interest you, feel free to ask about those. And then Google sent us a note earlier today asking us to direct you all to haveasec.com/io. And if you go there, you put in the time slot and a session, and you can give feedback. So we'd appreciate any feedback you have for us. And with that, we will move to questions. So,
two-part question about your counters. Why did you still shard them when you put them on memcached?
There actually can be contention with memcache when you're hitting it very intensively.
How many requests per second would you put that? Or?
I don't know. Do you guys recall?
Well, we found that once we hit there's a couple reasons we charted the memcache counter originally. One is there is that possibility of contention. Another is it's cheap to make lots of memcache shards. And one of the issues I mentioned in that slide is that as you're writing the shard to the data store, you might not get a response back for a half second to 4 seconds. So all of that time, you're having a lot more requests coming in. We wanted to minimize to some degree in order to keep the count a little as accurate as possible, that very, very small time frame from when we clear the memcache shard as, okay, we got a confirmation back and then we've written it out. We don't want 30 new requests coming in that time frame because there is still a little bit of latency even writing to memcache. It's much, much faster than writing the data store. And so by making lots of shards, it's not really any overhead for the system, but we can sort of spread out the number of requests and that just a couple of milliseconds, it's less likely we'll lose something. Does that make sense?
Okay. The second part is, before this morning, I didn't really know how many memcached instances Google would have for my app. But now it sounds like I have to assume if I write to a key, it will always be the same one memcached, because otherwise these counters wouldn't work. If I have one instance of my Java app running in Australia.
No, that's correct. Memcache is a distributed API. And so if you write on, you don't have any knowledge of what CPUs your code is executing on inside the App Engine data center.
Right, but now it sounds like I have a guarantee that when I write to memcached, all my 500 app instances write to the same memcache
they're effectively
instance.
writing to the same store. That's correct.
Do you think that will be future-proof?
I don't know how they propagate that data across. I don't know how long it takes. So if you're running code, not that you can specify when you're writing an App Engine application right now, but if some of your code's running in Australia and some of it's running here, I don't know how long that would take to propagate. But yes, it looks like you see a consistent view of the memcache world, regardless of where your code is.
I'm just surprised that that's future-proof because, once you get to the Facebook scale, maybe you guys you need multiple memcached instances for the same write. Okay.
Yeah, well, I mean, we've had good luck with it, but I'd say that's a really good question for the folks who actually built it would have better answers than we would.
They also have the memcache has a certain size, and the more you put in there, the more you increase pressure on your memcache, and the sooner things will expire from it. So there's really a balancing act about figuring out which things to put in there, and the size of your entities matters when you're putting things in. So choosing that, you're making a lot of decisions that will affect how available that data is when you go back to look for it later.
I think there's one actually small thing I should mention on that, which is that when you write to a memcache, I believe it gets deleted first created, first out, not last updated out. And so when we refresh our memcache key, I believe we delete the key and then recreate it rather than just updating it. So that way it's got a fresher date and is less likely to get migrated should more contention happen in memcache.
I have a couple of questions. First is about your API. You sort of had a very simple diagram, but the queuing that you do when you don't have the latitude and the longitude, does your API just return queued up? Like, I mean, in case the query is for a latitude and a longitude that you haven't calculated, do you just return queued up?
Yeah, that's right. Our API returns to the customer try back later, basically. And if you think about the typical use case of embedding in a real estate site, what that means is the customer doesn't display the walk score that time, but the next time one of their users comes and looks at that same property, we'll probably have that walk score queued up and ready for them.
Okay. Yeah. And the other question is about, you use this metric of queries per second. So when you were describing the techniques to speed up, like using memcache and everything.
Yeah.
So this queries per second, I'm assuming, is like data store queries that you're saying, right?
Oh, no. When I was showing those queries per second numbers, what I was showing is the number of successful URL requests that someone outside of the App Engine data center can make to our application and get running correctly. And those numbers were rough. They won't apply to your application exactly, but that's approximately what we saw in the development of the WalkSquare API.
They're also a little bit better now.
Yeah,
I think if you were to write the same app that we did early on, you would get, I think, a much higher queries per second today than 8 months ago.
Yeah, I mean, the bottom line message is that even with naive code, you can actually scale out pretty far with App Engine. It's pretty impressive.
I have two questions. The first one is, are you now running your entire production front end off of App Engine?
Yes, we do.
So if we go to www.walkscore.com, it's actually...
Oh, right.
No, we're only doing the API there. We are looking at, we're considering moving other parts, either the tile or potentially even the whole website over. And I don't know, you could mention quickly the Kocher stuff.
Yeah, yesterday, so the WalkScore website is also actually written in PHP. And as you know, JVM now on App Engine. And there's a company here called Kocher, which makes a PHP implementation for the JVM. And actually yesterday, we just were able to port our entire PHP website over to App Engine. And we just started testing it, but it looks like it's extremely performant, which is impressive. It's a lot faster than running Apache on a private server at some random ISP. The API itself, however, is all, of course, Python and App Engine code.
And the second question is, have you run into any of the big limits of App Engine in terms of the storage indexes you mentioned in your last slide? Have there been any big things where you end up having to be billed for a lot more than you expected?
We haven't. They gave us, as early users of early high traffic users, they gave us access to go beyond those initial free quotas, before the billing was enabled. Now that billing is enabled, there's a lot more flexibility to go. You can use a lot. So we haven't really run into any of those limits. I think the things that are interesting are the per request limits of how much CPU time you can use and how much time you can use. And we have some of the EC2 to App Engine communication. Some of those things they use way more CPU time than App Engine is really happy with. But because they're much less frequent than the public calls that come in at a much higher rate, we can manage those, and we use some backing off techniques where if EC2 has trouble communicating, it can say, oh, we're gonna stop talking to App Engine for a little while, stop hitting it with these high CPU intensive requests.
Do you want to take this?
Sure.
Considering that calculating walk scores requires considerable time, would you consider using webhooks? And actually, I was in Brett's talk just previous, and the answer is yes. I think we'd love to use webhooks. We haven't used them yet, but it might be something for us to look at. And certainly, for those who were there, I think you can probably guess that a lot of our calculator code fits nicely with the task queue API that he described.
Yes, go ahead.
Could you please elaborate a little bit into how you implemented how you implemented between the queries of your App Engine and the computational intensive part of Amazon EC2?
Sure. I mean, I can dig a little more into the design of the calculator. Basically, the calculator is currently, wow, okay, we got a bunch of random stuff. So the calculator is, of course, completely running on App EC2. Right. And it's actually running on a single machine, but it's lots and lots of processes.
Do you want to jump to a slide in here?
Actually, I wanted to jump to that one. And so the key thing that we saw, because of the unpredictable performance reading from the queue that we've implemented on the App Engine side, is that we wanted to decouple the computation of a walk score from the I/O requests we made. So what we have is a master process that spawns off a ton of slaves. Some of those slaves are responsible for talking to App Engine and requesting new latitudes and longitudes that we need to calculate. And what we do is we have a rather large buffer on the Amazon EC2 side of latitudes and longitudes coming in, so that if we can't talk to App Engine for a while, we can continue to calculate scores. So that's one major thing. We basically decoupled our I/O from our computation on the EC2 side, and we buffered all our I/O. And sort of one last point, which Jesse alluded to, is that we dynamically respond to the changing I/O conditions. So if App Engine if contention is very high for more than, say, 10 or 15 requests in a row, what we do is we actually back off and stop talking to App Engine for a while. And for various reasons, based on the internal design of the data store, that's something that can actually alleviate contention if we come back 20 minutes later, and just work through the data that's buffered on the EC2 side. So that's sort of the big picture of the design of the calculator.
All right, so it was roughly one database, and you used rsync or something like that between.
Oh, so actually, App Engine is our data master. All of our data is there. All of the points that we're working on the EC2 side are simply held in RAM. If that process crashes, it's not the end of the world. We basically might redo a few points. The EC2 code is also Python. So if we accept out of a process, we actually just pickle out all the current data. So.
Okay. Thanks.
Yeah.
Any other questions?
We have moderator questions.
That was the only one.
That's it.
Oh, well, thank you.
Thanks, guys.
Yep. Thanks, guys.